Alright, last section of the Year 11 course, we're going to talk about this thing called entropy, which is somewhat related to enthalpy, but different word, entropy, and something called Gibbs free energy we're going to end the course on. Don't get too excited, it will never go away. Nothing in chemistry ever goes away. Okay, so how can enthalpy and entropy be used to explain reaction spontaneity? And that's what we're getting to. We've got the knowledge about enthalpy from the first two chapters. So we learnt about endothermic and exothermic and things wanting to get rid of energy and be at a lower energy. And now we're going to couple that with entropy, and they come together to talk about reaction spontaneity, or when you put stuff together, does a reaction happen or does it not? Because we know sometimes it does and sometimes it doesn't. So this is giving us the tools to quantify and determine, also qualify and quantify words, that if a reaction will happen. Okay, so let's I put in here stuff about spontaneous and non-spontaneous reactions. Let's see what I've written. A spontaneous reaction is a physical or chemical change that occurs without any input of energy or materials from the outside. The way I like to think about it in my own words is, if I shove these things together, is something going to happen? Okay? If something happens, it's spontaneous. If it doesn't, it's non-spontaneous. Okay? So a non-spontaneous reaction is a physical or chemical change that will occur with an input of energy and materials. Okay, so you need to put energy in there or something else to make it happen. Okay? So we saw examples when we were studying galvanic cells. Remember how there was only one way that you could hook up the cell, and hooking it up the other way resulted in nothing. Okay, so we looked at, if the cell works, it was spontaneous, and we looked at the conditions, and we looked at the standard cell potential table to make a spontaneous reaction. Okay, only certain combinations would result in a voltage. Okay, another good example is nitrogen and oxygen in the atmosphere. Now, thankfully, that's a non-spontaneous reaction, because we'd have no nitrogen and oxygen free in our atmosphere. We'd all have nitrous oxides and stuff like that instead, but we've got free oxygen because the nitrogen and oxygen is a non-spontaneous reaction. It needs a lot of energy to get it going, for that to happen. And there's one main way that can happen before humans came along, and that's my picture of lightning here. So lightning is a large input of energy. So lightning it provides enough energy for this non-spontaneous reaction between nitrogen and oxygen to occur. So you actually get like nitrogen monoxide and all types of things happening in small amounts around lightning strikes. But now with humans coming along, we've got energy stuff, words, so around power lines and stuff like that. Also, the main one is around internal combustion engines. Okay, so internal combustion engines have enough energy and heat around them to take nitrogen and oxygen and turn it into nitrogen monoxide and stuff like that, and they take part in a series of reactions that contribute to smog, okay, along with ozone as well. So that reaction is a good example of non-spontaneous, that once provide enough energy, it can occur. Alright, so let's reframe enthalpy and talk about this enthalpic drive. Okay, this word that I'm talking about here. All of my GIFs are not working, but Ralph rolls down the hill, water goes downhill. These are all expressions of potential energy and going downhill, okay, and releasing energy. So we know from everyday experience that most chemical and physical changes tend towards lower energy, and we've been picking up that all throughout the course, that things like to be nice and stable and give away energy, or have the most energy in their bonds and stored away, to be the most stable. Okay, so so I often say nature is lazy. So a ball will roll downhill, or a water falls from the top of the cliff to a space, because The down the bottom has a lower potential energy, okay? A spring will expand after being compressed, which is still potential energy, but kind of going back. A spring will expand because it wants the least deformation or the least potential energy. Excited electrons will emit photons. So electrons in outer orbitals, once they can get to a lower energy, they'll drop back down and emit photons, okay? And also combustion reactions happen in our atmosphere as the products are more stable, okay? So we talked about that with combustion reactions. Things will combust and a lot of energy will be given out, and the carbon monoxide and water product of these is much more stable or lower energy, okay? So processes that reduce in enthalpy or are exothermic or delta H less than 0 are said to be enthalpically driven, okay? Nature wants to go this way, all right? So the enthalpic drive is the drive to release energy or have an exothermic reaction or enthalpy less than 0. Nature loves enthalpy less than 0. Those processes it really likes. Okay, but the trouble is, if that's so true, we've seen some spontaneous endothermic reactions, haven't we? So these reactions that we looked at where we dissolve some salt in some water and it took in energy, or you do a chemical reaction like the ones in a cold pack and it takes in energy, that's going against this drive, but it still happens. So the enthalpic drive is not the only thing that makes chemical or physical changes happen. There must be something else. Okay? There must be something else at play here. And this thing, if you're guessing, is the thing called entropy. Okay? So let's start looking at that. Excuse me. So, the universe that we live in, as opposed to the universe that we don't, I don't know. There could be. Let's not go down that avenue. The universe that we live in tends towards disorder or randomness over time. Okay? So, not actually a true example, but kind of, but not really. Your bedroom becomes messier over time. Okay? Becomes more disordered over time. If you release a gas at one end of a room, it will dissipate and dilute. There's a fancy word for it. What is it? I can't remember it off the top of the head. But it will dissipate throughout and mix in that whole volume of that room. Okay? It won't just stay in that corner. So to counteract disorder in the system, to counteract this, we need to tidy up our bedroom. Okay? Or clean up. With a gas, that's really hard. You've got to do a lot of physical separations and stuff to get that gas back by itself in a canister. It's really hard and it takes a lot of work. Okay? So, the entropic drive, contrasting it with the enthalpic drive. So the drive towards disorder or randomness is called entropy, and sometimes we call that process the entropic drive. Entropy is a measure of disorder in a system. Okay? Processes that increase entropy are said to be entropically driven, and nature likes that. Nature likes that randomness. Okay? Another way to think about entropy is the tendency for energy to dissipate in random ways or spread out or dilute. Energy and matter spread out and diluted. I like that definition for entropy more. It helps me. And it's usually as heat. Heat spread out in different molecules, little wobbles, little stretches and stuff, all throughout matter. So heat that is spread out in space with different molecules, a little bit of heat everywhere. It's hard to capture and hard to use to do stuff because it's so dilute and spread out. Okay, so heat spread out is the ultimate goal of entropy. Okay, we can't use it to do anything. All right. The net entropy of an isolated system will always increase. Okay, we're going to a more formal definition, and this is linking to some, which is beyond this course, the laws of thermodynamics, or how heat and energy behaves. Okay, so if you have an isolated system, remember, we haven't really talked about an isolated system. An isolated system cannot exchange matter or energy outside the system. Okay, so if you have a completely enclosed space for matter and energy, the entropy within that will always increase. Okay. Oh, look, I said it there. The second law of thermodynamics. Thanks, past Mr. Roberts. So the entropic drive results in an increase in entropy/disorder. Okay. Most spontaneous processes, so most chemical reactions that are spontaneous and physical changes result in an increase in entropy. Okay, most, not all. So if you leave a bucket of water outside to evaporate over time, it will disperse throughout the whole atmosphere, those water molecules. If you combust wood, it results in a lot of different gases, so carbon dioxide and other stuff, and they disperse throughout the atmosphere. And if you dissolve a spoon of salt, it changes from an ordered organic, so in that crystal lattice substance, and it disperses in a large volume of water as separate ions. It gets very disordered and messy. Okay? Processes that do decrease in entropy, or go the opposite way, or go against the entropic drive, do occur. Okay? But they occur within the system, and they're like concentrated pockets. Okay? And to do that, to get a decrease in entropy, there'll have to be areas outside that increase in entropy. Okay? So net overall in that system, you get a increase in entropy. But we've got processes here on Earth or out in space, some processes that do it, but it takes entropy away from other. There's always a cost. Okay? For example, frost will form from gaseous water on a cold morning due to the enthalpic drive. Okay? So the enthalpy of losing energy to become a crystal solid for that water overcomes the entropic drive of suddenly becoming more ordered. Okay? But only under certain conditions. Yeah? You need the right temperature and pressure conditions, don't you, for frost to happen. So spontaneity of a reaction is a battle between the enthalpic drive and the entropic drive. It's a battle between the two. Okay? Don't know if battle's a good word. Sometimes they work together. Sometimes they work against each other. Yeah? We'll get to that. Okay, here's a bit of a black slide extension. So, consider the universe as a whole. As time passes, the energy in the universe becomes more spread out and diluted, or the heat. Okay? Enthalpically, every piece of matter wants to exist at the lowest energy state and dissipate its energy. Entropically, all energy is dispersed and diluted through the whole universe as useless heat. Okay? So our sun will die. That energy that's there, that chemical reactions, the nuclear reactions will dissipate. It will pass on its matter to something else. It'll have less energy. It'll pass on its heat out into space. It will become diluted, and generations of stars and galaxies will form each time with less and less available energy as it's being spread out. Okay? Eventually, we're going to get to a universe where all matter is dispersed, and each little matter has a little bit of energy, but not enough energy to do stuff, not enough energy to react or physically change. Nothing will happen, all life will cease, all chemical reactions will not occur. And we have a special name for that. It's called the heat death of the universe. And it's very cheery in some ways. I'm being a little bit sarcastic, but yeah, I think it's beautiful in its own way. Okay, this video is so good about thinking about entropy, and it starts to introduce talk about probability, which we'll get to right now. Okay, so qualitative entropy. So our understanding of matter and atoms and how they're arranged, we can qualitatively estimate entropy changes in energy and matter. And we use the symbol capital S for entropy. And so therefore, if we talk about changes in entropy, we're using the symbol delta S. So kind of like delta H for enthalpy, we talk about entropy as S and the change in entropy as delta S. Okay? The change in entropy in the system. The main qualitative estimate we have is using the particle model and a comparison of states, okay? So think about the orderedness of a solid, okay? All lined up, all nice and ordered, low entropy, okay? If you heat that solid up, it becomes a liquid, so they're all the particles are still really close to each other, but they can move about, okay? We're only overcoming some of the intermolecular forces there, okay? So we're increasing the entropy, all right? Because it's less ordered. If we heat it up again and change it to a gas, we've got big gaps between it, okay? And we've got a lot more randomness in there too, okay? So highest entropy of all the gas. So entropy increases from a solid to a liquid to a gas. Okay, although different solids, when you compare solid to solid, or you compare liquid to liquid, they have different entropy values. They only differ a small part, okay? Compare that to the difference in entropy between solids, liquids, and liquids to gases, okay? That's the large change in entropy. So the magnitude of entropy change from a liquid to a gas will always be much greater than the change from a solid to a liquid as well, okay? Because of this change in orderness. So solid to liquid, you've only got a small change in entropy here, okay? So let's look at this lovely graph where we're increasing temperature and we're looking at the change in entropy. So as you increase temperature of the solid, it becomes slightly less ordered, a bit more wiggles and stretches and stuff until it gets to a point where it changes state and it melts the solid. Entropy increases, but temperature doesn't increase, okay? It's that latent heat stuff, okay? And then once it's a liquid, it's going to slightly change, okay? Notice that this is only a small change. I shouldn't be using red on the red there, but it's only a small change in magnitude compared to this larger change. Also, look at the size of this evaporation change in entropy. It's much larger than the melting change, okay? That's to go with the kind of the craziness or disorder of a gas, okay? Much more disordered. Okay, probability. So another way to frame entropy is to think about it as a probability problem. And that TED Ed video before goes brilliantly into that idea, but let's bring it up here, okay? So if you drop a pile of 20 bricks, there are many different ways that they can fall, okay? One option is they fall into a perfect brick wall, okay? Imagine randomly dropping 20 bricks and you see a brick wall there. That's perfectly fine. But that's very improbable. That never happens. But it's within the realms of possibility, okay? But what's more probable is some random disordered pile of bricks, okay? There's billions of ways that you can drop these bricks. There's billions and trillions of them, and like very small, or if one results in a brick wall, but many of them result in just a crazy pile of bricks, okay? So each of these possible end things, so if you're dropping a random pile of bricks, each of these possible rearrangements of this brick is called a probabilistic state when we're talking about entropy and matter, okay? There's many of them dropping bricks, and only a minute fraction or one of them will result in a brick wall, whereas most of them are just piles of bricks that are useless, okay? So you can also think about if you have a jar that has a barrier in there and you've got these green particles above and these yellow particles below, if you take that barrier out, what's going to happen? They're going to mix through each other. Why? Because there are many possible ways to arrange those particles in that box, and only one in trillions of billions would actually be all the greens up the top and all the yellows down the bottom. So we don't see it happening spontaneously where all the greens go up the top and all the yellows go down the bottom, because one out of billions of trillions of possibilities is that actually occurring. All the others are some random mixture, okay? So that's why we see that happening. Another qualitative way that we can estimate entropy change is to compare the number of molecules in the reactants to the products of our chemical change. Okay, so this comparison is smaller than what we'd see between the states, but it still gives us an idea of what's happening. And it only works for homogeneous reactions, okay? Because the entropy change between states and stuff like that is much bigger. But if you've got a homogeneous reaction, and you can compare molecules to molecules, okay? For example, here's the combustion of hydrogen. We've got two H pluses and one O2 going to two molecules of water, okay? On the left-hand side, you've got three gaseous molecules. On the right-hand side, you've got two gaseous molecules. Now, if you think of a space, and let's just put it with three molecules in there, there's many ways that you can arrange those three molecules, okay? Now, once it goes to its products, its two molecules of water, there's less ways that you can arrange two things than you could have arranged three things. So for this reaction, entropy is higher with three molecules than with two molecules. And that will work with all homogeneous reactions as well, okay? So this reaction here, entropy decreases because you're taking three gaseous molecules and you're forming two gaseous molecules. Okay, so with homogeneous reactions, you can compare and do like a counting of molecule to molecule to see what happens. So we've got 3 mole versus 2 mole, so entropy, the change in entropy is less than 0, or it decreases. If we're going with a reaction with 2 molecules on the left to 3 molecules as the product, entropy would increase. There's much more ways to arrange those 3 molecules, okay? So that's another way we can, excuse me, estimate entropy. All right. So here we need to analyze the difference between entropy and enthalpy, and we've kind of been talking about it, but I pulled this table in this diagram out. Okay, so enthalpy is denoted by the H, okay, and it refers to a measure of the heat content in a system, okay. Remember the constant pressure and stuff like that, but it's not big. If you talk about the heat content, you're doing pretty good. Entropy is denoted by S and refers to the measure of level of disorder in the system, okay. So heat and disorder. So we're talking about how much heat there is changing in a system, and entropy is talking about heat and matter that is dispersed or distorted, okay? So enthalpy is a kind of energy. Entropy is a property of energy. Here, enthalpy, it's a sum of internal energy, okay? It's a measure of randomness in the molecules and energy. So down is denoted by H, denoted by S. I didn't know this. It's termed by a scientist named Heikki Kamanonis. Maybe that's where the H comes from. Rudolf Clausius. I've heard of him before. Don't know why they chose S. Okay, units. Here's another thing that we haven't talked about. Joules per mole or kilojoules per mole for entropy. Joules per Kelvin for entropy. Okay? Okay. Enthalpy is only applicable in standard conditions, so standard temperature and pressure. Entropy can be applied to any conditions. Here's the big one. A system favors minimum enthalpy, or it wants to decrease in enthalpy. Okay, that's the enthalpic drive. The system favors maximum entropy. It wants maximum entropy. Okay, those two things. Okay, here we go. Use modeling to illustrate entropy changes in reactions. Here's one of my models that hopefully will help you out. Okay, we're getting to the end of this video. I really like this though. So, we can use a 3x3 grid to represent a volume for our little model. And we can use 4 of those cells, 4 of those 9, to represent particles. Okay? And we can set different rules to model solids, liquids, and gases and see what happens. And what we're going to get is probabilistic states popping out. Okay? So, probabilistic states, sometimes called microstates. So for my model here with my 3x3 grid that has 4 particles in them, which I've represented by red, okay? So the empty ones are the grey. So for a solid, I'm setting the rule as, trying to emulate a solid itself, it's 4 red boxes, and they must be arranged in a grid-like pattern. So there must be 2x2, okay? To represent the grid-like regularity of a solid. Now there's only four possible ways that I can colour in 4 red squares that are 2x2 in a 3x3 space. Okay? Top left, top right, bottom right. Okay? So there's 4 probabilistic states for my solid rules in my model. Okay? Now let's contrast it with going to a liquid. So using the same model, my liquid now, to try and emulate a liquid, is liquid. The particles are still very close to each other like in a solid, but they can freely flow. So how I'm representing that is that the 4 squares must be touching each other, okay? But they can form any shape. They don't need to abide by the 2x2, okay? So what ends up happening now is these combinations that I get are 24 of them. Okay, and that meet that criteria. For example, we've got this Tetris-like thing here, or all of them are Tetris-like, aren't they? Okay, so we've got all these different shapes arranged in different places, but none of them fit the solid criteria, and they all fit the criteria that they are 4 red boxes that are all joined up, so all the particles are close together. So I've got much more rearrangements here, haven't I? Much more probabilistic states, 24 compared to the 4, okay? I'm getting a lot of more randomness in my model. Look at this. I've made gases. So here I'm trying to model using my same ideas, but here I'm modeling in gas and I've let go of all the rules, okay? I just need 4 boxes that are coloured in that are not solids or liquids, okay? And it gives me many, many more possibilities. Look at these. 96. Okay, 96 more possibilities there. Okay, so as a gas, you've got a lot more randomness because there's a lot more ways to rearrange it. Okay, so just within my 2-dimensional model, where I've put some simple rules in, I can see and demonstrate entropy and why the relaxed rules of gases end up with more probabilistic states. Okay, so here I've got them all. I've got my solids down here. I've got my liquids here where we had 24 states, and gas-like states had 96 possibilities. And so entropy is increasing up this way. Okay? So that was nice and simple, a 3x3 2-dimensional grid. Now, I just want you to imagine, now my GIF won't work, but you know the GIF. Imagine this grid is 3 dimensions, and let's just put 1 mole of particles in there, just to keep it simple. Or 6.022 times 10 to the 23 boxes on each side. You can imagine how much randomness and disorder is coming into matter. It's an awful lot. Okay, here's a question that I've stole. Look what happened to the text. Which one is more disordered? The glass of ice chips or the glass of water? I'll leave you to think about that. Okay, last couple of slides. This one's just talking about, it's from the textbook, talking about the randomness or the disorder in the different states. Now, the only thing we haven't talked about is another common state that chemists talk about is solutions, okay? So dissolution always involves an increase in entropy. And the way to think about it is, down here, you've got the solute and solvent separated, and up here you've got some random mixture. And you have to think all those different ways that you can arrange that solution is much more than how you have to arrange the solute and solvent. So that's why it always results in an increase in entropy, okay? And also, have a look here, you've got an ordered, now this is a dissolution of an ionic solid, so highly ordered there, and the water's fairly ordered. It hasn't got anything mixed between it, somewhat ordered, not as ordered as this crystal lattice here, but just think about what happens when you get the ions surrounded by the waters and just the different ways that you can arrange them. Okay, so more entropy as the dissolved thing there. All right, that's enough. We've talked through the theory of entropy. Next video, we're going to start estimating entropy changes in reactions.